Hey class, just a quick video here. I'm going to go over the technique of finding the centroid of a group of forces, that is the equivalent force that has the same net effect on a structure as the other forces independently acting. We'll be going to be doing this by graphic techniques and also algebraically through the summing of moments. These are two techniques that we'll be using in the class this semester, so you can review this video at your leisure. And without further ado, here we go. Alright, so to begin with, let's just recap this notion of vector addition, that if we have two forces, such as these two in a linear sense, we could say that maybe this is 100 pounds and this is 100 pounds. And so the net effect is going to be 200 pounds. So this is being drawn at a scale, and I've got 1, 2, 3, 4, 5 squares. That means that any individual square in this case is equal to 20 pounds, because 20 times 5 is 100. That would be our scale. And so that's a graphic method of addition. We also know about finding the centroid of forces, not centroid forces, the resultant force, by vector manipulation using the parallelogram law. So if I have two forces here, let's say this one is going to be a 100-pound force, and this one is going to be a 100-pound force. The resultant of these two is found by the parallelogram law. It says that the resultant force is the one that goes along the diagonal from a line that's drawn parallel on either side of the original forces. So again, I'm using the same scale here. To get out my scale. So there is our scale, that this is 100 pounds along here. This is a 1 to 10 scale. So we will note the scale. It's 20 pounds rather. 1 inch is 20 pounds. So we can then measure this directly, and we see that we've got 100, 10, 20, 30, 40, and a little bit more. So we'll say about 140 pounds. Now we can also do this algebraically with trigonometry and recognize that this is a 1-to-1 ratio on the slope. So a 1-to-1 is, let me draw that out, it's going to be 1, 1, square root of 2 because of the Pythagorean theorem. Remember that a squared plus b squared equals c squared. So c is then the square of the sum of the squares. Or in this case, c is going to be equal 1 squared plus 1 squared. C equals the square root of 2. That's how we get that square root of 2 at that point. So the square root of 2 is to this force in the same ratio that 1 is to 100. So we multiply the square root of 2, which is 1.41, multiply that by 100, or 10, and we get our 140 pounds of force. Now, working with vectors that are at an angle, we can do these type of manipulations very directly. But what's the resultant from two forces that are parallel? Well, that's slightly different. It's a different technique, so we're going to do the same one we did in class. I've got two forces here that are parallel, and I'm drawing them to the scale of the force on this diagram. So this is going to be, we'll say 200 pounds, and this is 100 pounds. And again, the scale (1 inch) equals 100 pounds. And I am just noting that I wrote that down wrong and up here. This is not 20 pounds. The little square is 20 pounds, but the 5 squares together, since there's 5 small squares, 20, 40, 60, 80, 100 pounds. That's where that comes from. So this is the technique we're going to use here. We create a second diagram associated with this. So we'll call this one our form diagram. And we'll come back to what that means as we go on in the class. But we also have what's called the force polygon. I'm going to draw that over here. So the force polygon is going to have the same basis as the form diagram. In other words, this is 200 pounds plus 100 pounds, or 300 pounds. So let's see if I left myself enough room to do this. Go back to my scale here. I'm going to just squeeze this in, just barely. So from here to here is my 200, and there another 100 right there. So I've got 200 pounds here, 100 pounds here, for a total of 300 pounds. Now here's the technique. We can pick any point on either side of this line. I'll do it on this side because I don't have any room over here, but it would work the same on the right-hand side as well. Just pick any old point and then draw lines from the tip and tail of each of those vectors to make this kind of radial diagram. So this technique involves a transfer between this diagram, the force polygon, and the form diagram. And this is where we need to be able to draw parallel lines. So this I'm going to do with a straight edge. I don't have a rolling ruler here right now. And what I want to do is just get an intersection point at that angle. What I need is that angle and this point. And from there, I need to get from what's called the line of action of this force. It's an infinite long line. I want to take this line, transfer it over here till it intersects this line. So once again, I'm going to use my triangle. And I get an intersection point over here. That's an important point. And then lastly, I need to get this angle and have it cross over the second force because I have two forces here. So we'll get this aligned up. And here we go. Now here's the final part of this. What I want to do is project this line up and project my first line up until they intersect right here. That point, since this total thing here is equal to 300 pounds, that point is the location of that resultant force. It's the one force that combined at this point would have the same net effect on the overall system. In other words, I could use that one force there and an object would remain in balance. The distance across here is simply a measurement at this point. So if I say that this is 5 feet across here, if there's 1 square for every foot on this paper, then the distance between these is going to be 10 feet. The distance to here, I simply measure this, and I've got about 1, 2, 3, about 3.5 feet here, and that would leave us with 6.5 on the other side. Now, this technique will explain later why this works, but for now, just get used to the process of doing it. And let's give this another try. See if I can get myself a colored pencil here. Do this one in red. Let's just pick another point. It can be anywhere. How about down here? So I'm just verifying what I previously had done. I should get exactly the same answer. So I want to start over here. Get that aligned. And I'll do this below the other one, just so it doesn't get confusing at all. Start there. It's where it crosses, again, the line of action. Then the next one, down here. Transfer that all the way across to here. And then the final one over here. That intersects here. And we extend that one up. Oh, that did not work. What did I do wrong? Oh, that's not the angle. What did I measure wrong? See that? It's easy to screw up. So this line has to be over here. And that's the angle that we want to transfer. Let's see if I can make it all the way over there with this ruler. That's why a rolling ruler is very easy. There we go. That's what I need. Pull this down here. Ah, now we're looking good. Look at that. Right on. Same point. Now, it may not fall exactly there. It just happened to land that way. This could be up or down. But what is important is that it's on this line right here. So that finds the balance point for two forces. Now, if you think about balance of an object, as we had discussed in class, that, say, this block of wood here, it has a balance point somewhere in the middle. And if there's weight on the side, maybe this little object here, that's going to tip to the right or to the left, depending on where it's placed. So the balance has shifted from the center over to the heavier side in this case. So there's rotation that's happening as well. If we pick a point on this structure and look at it rotationally, there's a force that goes here and a force that goes here. Now this doesn't have to be drawn to scale. This is 200 pounds. This is 100 pounds. Relative to this point, these want to rotate. So to balance this, I would need a counter-rotation that's equal and opposite, but it has to be balanced both linearly and vertically. So the sum, or linearly and rotationally. So the sum of the forces in the vertical direction is negative 200 pounds going down minus 100 pounds equals negative 300 pounds. To achieve balance, I have to have 300 pounds going up. So that's the sum of the forces vertically equal to 0. I've got negative 200 plus 100 pounds minus, or excuse me, that's down 100, plus this equilibrium force here, the balancing one. So the value of E has to be equal to 300 pounds. It's the total of what's going down. So for this system to be, this is linear equilibrium right here. Now for rotational equilibrium, slide this up a little bit. For rotational equilibrium to occur, the rotational tendency of this force relative to this point going in this direction and the rotational action of this force going in this direction has to be the same. So we would say the sum of the moments relative to, we'll call this O for origin, the moments about point O have to be equal to 0. That's a fundamental condition of rotational equilibrium. Now, normally, what we'll be doing is finding the magnitude of this resultant force, which is our reaction on a structure, because we have known distances. But in this case, what we don't know, we know the magnitude of the force, but we don't know where it acts. We're looking for this x. The one that we solved graphically here is 3.5 feet. So by summing moments, though, we can find that because everything is a force times a distance. So the 200 pounds acts right through the reference point. So its moment arm is 0. So we're going to write out this equation. And I'm going to call forces that rotate, have a tendency to rotate in a clockwise direction, positive. So that 200 pounds has a moment arm of 0 feet. So it actually just drops out. And you'll see by inspection in the future that we don't even need to write that down. But then I have another 100-pound force at 10 feet. So this is my force, and this is my moment arm. And together they're in units of pound-feet. That's force times distance, so it is a moment. Then balancing this, I have to have this force, the 300 pounds, acting at an unknown distance, x feet, has to be equal to 0. So the x is the unknown. By linear equilibrium, I determine the magnitude of this force. By rotational equilibrium, I'll find out where it acts. So the value is negative here because my presumption is that it goes up to balance the downward ones, and therefore its rotational tendency, it's not actually rotating, but its tendency to rotate relative to this point is going counterclockwise. I've called clockwise positive, therefore it's a negative sign. So it's a simple matter of solving this equation. So I have 300 pounds times x feet equals 100 pounds times 10 feet. So 300, x feet equals 1,000 pound-feet divided by 300 pounds. So I see my pounds are going to cancel. Feet are the units that I want. Get rid of a couple zeros here since they're the same. It's 10 over 3. So this is in feet equals 3.33 feet. So that's about 3.5 feet, which is what was done approximately with the graphic technique here. So x in this case is equal to 3.3 feet. That's its actual distance. And if we drew this very, very accurately, or if we use CAD, you could even try drawing this with a CAD program, you will get exactly 3.33 feet. And in a nutshell, that is the graphic technique for finding the centroid of a couple of forces.